Tonight, we're going to explore something that sounds simple on the surface. A distance, a number. How far away is the nearest black hole? It sounds like the kind of question that should have a clean, reassuring answer. Something like, very far away, don't worry about it, go to sleep. But here's what most people don't realize. When scientists started looking for the nearest black hole, really looking, with every instrument they had, the answer they found didn't reassure anyone. It disturbed them, because the nearest black hole wasn't where they expected. It wasn't the distance they calculated. And when they looked even closer, they found something that no one had predicted. The first surprise was the distance itself. It was far closer than the models suggested it should be. The second surprise was what the black hole was doing. It wasn't sitting still in empty space, the way most people imagine. It was moving. And it had a companion, a star it was quietly, patiently, invisibly feeding on. The third surprise was what happened when astronomers started looking for more of them, because they found them, many of them, closer than anyone had ever thought to check. And the fourth surprise, the one that genuinely unsettled the physics community, was what this meant about the number of black holes that must exist inside our galaxy alone. By the end of tonight, you're going to understand not just how far away the nearest black hole is, but why that distance is far more complicated, far more layered, and far more unsettling than any simple number could ever convey. You're going to understand what black holes actually are, how they form, why we almost never see them, and what it means that our galaxy is filled with millions of them, drifting silently through the same space we call home. Before we dive in, if you're someone who finds peace in understanding the cosmos, who trades daily anxiety for cosmic wonder late at night, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making content for people who think the universe is worth understanding. Now, let's begin. Let's start with what most people carry in their minds when they hear the word black hole. The image is almost always the same, a swirling vortex of darkness, a point of infinite gravity, something that pulls everything in and lets nothing out. A cosmic drain at the edge of space, something enormous, visible, dramatic, easy to locate. This mental image is understandable. It comes from decades of science fiction, from illustrations in textbooks, from the famous photographs of M87's supermassive black hole released in 2019. That glowing orange ring with the shadow at its center, perhaps the most shared scientific image of the modern era. It's spectacular. It looks enormous. It looks like something you couldn't possibly miss. But this image, while beautiful and technically accurate for a certain class of black holes, creates a deeply misleading impression about most black holes, and it almost certainly shapes how we think about their proximity to us. So before we talk about distance, we need to understand what we're actually measuring the distance to. There are several types of black holes in the universe. The one in that famous photograph, M87, is what astronomers call a supermassive black hole. It contains roughly 6.5 billion times the mass of our Sun. It sits at the center of the M87 galaxy, which is approximately 53 million light-years away from Earth. It is, by any reasonable measure, unimaginably far away, and it is not relevant to the question we're asking tonight. It's called Sagittarius A. It contains approximately 4 million solar masses. It sits about 26,000 light-years from Earth. Astronomers have watched stars orbit it at speeds exceeding 5,000 miles per second. Orbital paths that can only be explained by an invisible object of incomprehensible mass sitting at their center. Sagittarius A is real, confirmed, and thoroughly studied. It is also approximately 26,000 light-years away. This too is not the black hole we're discussing tonight. What we're discussing tonight is a different category entirely. The quiet ones, the invisible ones, the ones that don't announce themselves with glowing accretion disks or jets of plasma shooting across the galaxy. These are stellar mass black holes, objects typically between about 5 and 100 times the mass of our Sun, formed when a massive star exhausts its fuel and collapses under its own gravity. They are small by cosmic standards. They are dark, They emit no light of their own, and unless they happen to be actively consuming nearby material, they are essentially invisible to our instruments. It is this class of black hole, stellar mass, quiet, isolated, that we need to understand when we ask the question, how close is the nearest one? Because the answer to that question is not 53 million light-years. It is not 26,000 light-years. It is far, far closer than either of those. And depending on how you define nearest and how thoroughly you've looked, the answer keeps getting smaller. Let that settle for a moment. To understand why stellar mass black holes exist in our cosmic neighborhood, we need to understand how they're made, because the process of their creation is inseparable from understanding where they end up. Every black hole of this type begins as a star, but not just any star, specifically a star with considerably more mass than our Sun. But as a working number, astronomers generally say that a star needs to begin its life with at least about 20 times the mass of our Sun in order to end its life as a black hole. Stars below this threshold end their lives differently, as white dwarfs or neutron stars, which are fascinating objects in their own right, but not the subject of tonight's story. So, a massive star, say 25 times the mass of the Sun. It ignites, as all stars do, through nuclear fusion at its core. Hydrogen atoms are slammed together with sufficient force and heat that they fuse into helium, releasing tremendous energy in the process. This energy creates an outward radiation pressure, a kind of perpetual explosion outward that precisely balances the inward pull of the star's own gravity. For millions of years, these two forces hold each other in perfect equilibrium. The star burns steadily, but massive stars burn their fuel ferociously. Where our Sun is expected to live for approximately 10 billion years, a star 25 times its mass might last only 7 or 8 million years before the hydrogen at its core runs out. And when that happens, the balance tips. The core contracts under gravity, which raises the temperature, which triggers the next stage of fusion, helium fusing into carbon and oxygen. This provides a new source of outward pressure and buys the star more time, but each subsequent stage of fusion lasts a shorter period than the last. Carbon fusion, neon fusion, oxygen fusion, silicon fusion, each stage burning faster, hotter, more desperate. And then the star reaches the end of the line. Silicon fusion produces iron, and iron is where stellar fusion stops. Iron is the most stable of the common elements. It sits at the lowest point of the nuclear binding energy curve, meaning that fusing iron together doesn't release energy, it consumes it. The star has spent its entire life fighting gravity with the energy of nuclear fusion, and now, at its core, it has produced a material it cannot burn. In less than a second, in something closer to a fraction of a second, the iron core of a massive star can collapse from the size of Earth down to something roughly the size of a city. The infall is so sudden and violent that it triggers a massive shockwave propagating outward through the star's outer layers. This is a core collapse supernova, one of the most energetic events in the universe. A supernova can briefly outshine an entire galaxy of hundreds of billions of stars. But what's left behind after the explosion depends on the original mass of the star. If the collapsing core has the right mass, generally, if the remnant mass is between about 1.4 and roughly 3 solar masses, the collapse is halted by something called neutron degeneracy pressure. The protons and electrons in the collapsing core are forced together to form neutrons. The result is an object called a neutron star, extraordinarily dense, spinning rapidly, perhaps 12 to 15 miles in diameter, held up by the quantum mechanical refusal of neutrons to occupy the same space. But if the remaining core is more massive, if the original star was large enough, even neutron degeneracy pressure is insufficient. Nothing stops the collapse. The core continues falling inward, past the neutron star phase, past any known state of matter, until gravity wins completely. The result is a singularity, a point of effectively infinite density, surrounded by a region of space from which nothing, not matter, not light, not information, can escape. The event horizon, the point of no return, a black hole. Now, Here is the part that matters for our story tonight. When the outer layers of the star are blasted away in the supernova explosion, they travel outward in all directions at a significant fraction of the speed of light. But the core, the remnant, stays behind roughly where the star was. Not exactly. Supernova explosions are often asymmetric. The explosion doesn't go in perfectly equal directions. This asymmetry gives the newly formed black hole a kick, a natal kick, astronomers call it, that can send it drifting through space at anywhere from tens to hundreds of kilometers per second. But it doesn't travel far from where it formed. On the scale of the galaxy, it stays in roughly the same neighborhood, which means black holes are where the massive stars were. And massive stars are distributed throughout the galaxy, including in our own region of it. This is important, remember it. Here is the question that seems obvious once you've heard the setup. If stellar mass black holes are so common, why don't we just look for them? The answer reveals one of the most frustrating and fascinating aspects of modern astrophysics. Black holes, by their very nature, are defined by the absence of light. They are objects that absorb light and emit none. An isolated stellar mass black hole drifting through interstellar space, not actively consuming any material, not close enough to any star to create an accretion disk, is, for all practical purposes, completely invisible. Think about what this means. Our telescopes work by collecting electromagnetic radiation, light, radio waves, X-rays, infrared, ultraviolet. All of our instruments are fundamentally detectors of radiation, and an isolated black hole produces none. It is not like a dark planet that you might detect blocking starlight. It is far smaller than that, and far more likely to be an empty space where there is no starlight behind it to block. It doesn't emit heat in any detectable way. It doesn't glow. It doesn't pulse. It makes no sound. It broadcasts nothing. It just sits there, in the dark, waiting. This creates what astronomers sometimes call the visibility problem. We know, with quite high confidence, based on stellar evolution models, that the Milky Way galaxy contains somewhere between 10 million and 1 billion stellar mass black holes. The range is wide because the uncertainty is enormous, but even the most conservative estimates suggest tens of millions. The Milky Way is roughly 100,000 light-years in diameter, containing on the order of 200 to 400 billion stars. Black holes should be distributed throughout it, in the spiral arms, in the galactic bulge, in the halo. In our local region of the Orion Arm, where our solar system sits, there should be thousands of them within a few hundred light-years. But we can't see them. What we can see, the only method we have for detecting isolated black holes, is their effect on what's around them. And there are a few ways this manifests. The first is gravitational lensing. When a massive object passes between Earth and a distant star, its gravity bends the light from that star, causing it to briefly brighten in a very specific way. This is called microlensing. The brightness follows a characteristic curve. It rises symmetrically, peaks, then falls. And by analyzing the shape of that curve, astronomers can estimate the mass of the lensing object. If the object has a mass consistent with a black hole, but emits no light itself, that's a strong candidate. But microlensing detections are difficult. They require the black hole to be moving across our line of sight to a background star. They require precise photometric monitoring of millions of stars. They are statistical, probabilistic, and often ambiguous. A microlensing event tells you something passed in front of that star, and its mass suggests it might be a black hole, but confirming it is another challenge entirely. The second method is X-ray observation. When a black hole has a companion star close enough that the black hole's gravity is pulling material off the star's surface, that material forms an accretion disk as it spirals inward. The intense compression and friction in this disk heats the material to millions of degrees, causing it to emit X-rays. X-ray telescopes in space, like the Chandra X-ray Observatory or the XMM Newton satellite, can detect these X-ray signatures and identify them as black hole candidates. This method works, but it has a critical limitation. It only finds black holes that are actively feeding. The vast majority of stellar mass black holes in the galaxy are almost certainly isolated. Either they never had a companion star, or they consumed it long ago, or they're simply too far from any companion to be drawing material. These dormant black holes are completely undetectable by X-ray methods. The third method, The newest and perhaps the most promising is astrometry, the extremely precise measurement of stellar positions over time. If a star has an invisible companion, a black hole in a binary system, the star will wobble slightly as it orbits the common center of mass with its dark companion. This wobble is detectable with sufficient precision, and modern instruments like the Gaia Space Telescope have been hunting for exactly this signature. It was this third method, combined with the first, that led to the discoveries we'll now discuss. Discoveries that changed our understanding of how close the nearest black hole actually is. The history of searching for nearby black holes is a story of technology racing to catch up with theory, and of assumptions that turned out to be badly wrong. The first confirmed stellar mass black hole in our galaxy was identified in 1971. It was called Cygnus X1, named for being a strong X-ray source in the constellation Cygnus. At the time, the discovery was revolutionary. Cygnus X1 is a high-mass X-ray binary system, a black hole of approximately 21 solar masses orbiting a massive blue supergiant star called HDE 226868. The system sits roughly 6,000 light-years from Earth. For decades, it was the most famous black hole in the galaxy. The fact that something called a black hole could actually be detected, could leave an observable signature in the sky, was, at the time, a significant confirmation of general relativity's more extreme predictions. But 6,000 light-years is still quite far. In terms of our local neighborhood, Cygnus X1 is distant, and crucially, it was only detectable because it is an actively accreting X-ray binary, a black hole currently eating a companion star. It was the loudest possible version of a black hole, the easiest to find. Through the 1970s, 1980s, and 1990s, astronomers found more X-ray binaries. Systems like A0620-00, which lies about 3,300 light-years away and contains a black hole of perhaps 6 to 7 solar masses, feeding on a companion star, or GRS 1915+105, about 36,000 light-years away, notable for being the first galactic object observed to produce jets of material moving at apparently superluminal speeds, or V404 Cygni, roughly 8,000 light-years away, which periodically erupts as its black hole gorges on accreted material. Each discovery was exciting. Each one confirmed the existence of stellar mass black holes in our galaxy. But each one was found because it was actively emitting X-rays, bright, loud, consuming material. These were the easy ones, the small fraction of the total population that happened to be advertising their presence through intense radiation. The scientific community understood, even in the early decades of X-ray astronomy, that the detected population was a tiny, biased sample. These were not typical black holes. A typical black hole, the majority of black holes, would be sitting in silence, drifting through interstellar space with no companion star close enough to feed on. They were invisible to X-ray telescopes, and the assumption, for a long time, was that finding one of these dark, isolated black holes would require some extraordinary piece of luck, a perfectly aligned microlensing event, a fortuitous geometry of stars and instruments and timing. But here is where things began to change, and where the story of the nearest black hole begins to get genuinely interesting. If you had asked an astronomer to estimate the distance to the nearest stellar mass black hole, the answer would likely have been something in the range of 1 to 2,000 light-years, maybe a bit less if you were optimistic. The estimate was based on the known X-ray binary systems and on statistical models of how stellar mass black holes should be distributed galaxy. 1 to 2,000 light-years. That sounds very far. It is very far by any human standard. 88 trillion miles. 1,000 light-years is approximately 5,880 trillion miles, or about 5.88 quadrillion miles. No spacecraft we have ever built, moving at speeds we have ever achieved, could cover that distance in any timescale relevant to human civilization. So the answer felt comfortable, distant, unapproachable, safely irrelevant. Then, in 2022, a team of astronomers announced that they had found a black hole in a place no one expected. Using data from the Gaia Space Telescope, the European Space Agency's extraordinary astrometric mission that has mapped the positions and motions of nearly 2 billion stars with unprecedented precision, they detected something unexpected in a binary star system called Gaia BH1. Gaia BH1 sits in the constellation Ophiuchus. It consists of a Sun-like star, a G-type main sequence star, very similar to our own Sun, orbiting something invisible, something massive. The star wobbles in a perfectly regular pattern over a period of about 186 days, tracing an orbital path that requires a dark companion of approximately 9.62 solar masses, 9.5 times the mass of our Sun. Dark. No X-ray emission, no light, no signature other than the gravitational tug it exerts on its companion star. This is a dormant black hole, not actively consuming material, not forming an accretion disk, not emitting X-rays, just sitting there, bound by gravity to a companion star in a wide, stable orbit, and it sits approximately 1,560 light-years from Earth. At the time of its announcement, this made Gaia BH1 the closest known black hole to our solar system. The previous record holder had been roughly 3,000 light-years away. Gaia BH1 nearly halved the known distance. But here is the part that made this discovery truly significant, beyond just setting a new distance record. The system makes no sense, or rather, it makes no sense if you assume that the black hole formed through a standard supernova explosion. Think about it. The companion star, the Sun-like G-type star, is still there. It's still orbiting. If the black hole formed from a massive star that exploded as a supernova, the explosion would have been colossal. It would have radiated tremendous energy outward in all directions. It would have flung off a significant fraction of the binary system's total mass in the explosion's blast. Gravitationally bound to each other, the explosion would have sent them flying apart. But the companion star is still there, still orbiting, undisturbed. How? The astronomers who found Gaia BH1 considered several possibilities. Maybe the explosion was unusually symmetric and gentle, what some models call a failed supernova, where the star essentially quietly collapses into a black hole without the dramatic outward explosion. Maybe most of the mass fell inward rather than being expelled. Maybe the kick imparted to the black hole was small or directed in just the right way to keep the binary together. None of these explanations is fully satisfying, and none of them resolves a deeper problem. The evolutionary history of this system doesn't quite fit our standard models of binary star evolution. The companion star, at the distance it orbits, should have been engulfed or disrupted when its original companion star went through its red giant phase before the final collapse. The physics of how this system came to be as we observe it today is genuinely puzzling. This is shocking discovery number one. The nearest black hole is far closer than anyone expected, and it exists in a configuration that our best models struggle to explain. Let that settle. To fully appreciate the significance of Gaia BH1, we need to understand exactly what the Gaia telescope is doing and why it was able to find something that decades of other astronomical surveys missed. The Gaia telescope, launched by the European Space Agency in December 2013, is one of the most ambitious astrometric missions in the history of astronomy. Its task is conceptually simple: measure the positions and motions of stars with extraordinary precision. In practice, this means tracking approximately 1.8 billion objects across the entire sky, measuring their positions repeatedly over years, to an angular precision of micro-arcseconds. A micro-arcsecond is 1/1,000,000th of one arcsecond. One arcsecond is 1/3600th of a degree. The precision Gaia achieves is equivalent to measuring the position of a human hair seen from across the width of a continent. This precision matters for finding black holes because of what orbital wobble looks like at different distances. If a star has an invisible companion, a black hole, the star doesn't stay perfectly still. It traces a tiny elliptical path in the sky as both objects orbit their common center of mass. The size of this ellipse depends on the mass of the black hole, the orbital period, and most crucially, the distance from Earth. For a system like Gaia BH1 at 1,560 light-years, the wobble of the companion star is detectable only with the precision Gaia provides. A lesser instrument would see only a point of light moving steadily across the sky. It would miss the tiny superimposed wobble entirely. What Gaia essentially did was to take the positions of nearly 2 billion stars, track how those positions change over time, and then look for stars that don't move in a simple straight line. Stars that wobble. Stars whose motion describes a gentle ellipse superimposed on their general proper motion across the sky. Each such wobble is a potential flag. Something is orbiting this star, and by measuring the size, period, and shape of the wobble, you can determine the mass of the unseen companion. Most of the time, the invisible companion turns out to be another star, a dim one, or one seen edge-on, where the light is nearly blocked. But occasionally, the mass of the companion combined with the complete absence of light from that companion points to something far darker. When the team analyzing Gaia data found Gaia BH1, they did something careful. They checked for any light from the companion at all. Optical, ultraviolet, X-ray, radio. They found nothing. Not a faint star, not a neutron star pulsing radio waves. Nothing. The companion emits no radiation that any telescope can detect, and yet it has a mass of about 9.62 solar masses. Far too massive to be any kind of dim but conventional star, and far too massive to be a neutron star, which top out at around 2 to 3 solar masses. The only remaining explanation is a black hole. This is how you find a dormant black hole, not by waiting for it to eat something and broadcast X-rays, by being patient, precise, and systematic, by measuring the gravitational whisper it leaves on its companion star's motion through space. And Gaia BH1 was just the beginning. Astronomers had barely finished processing the implications of Gaia BH1 when a second discovery arrived. In 2023, the same approach, Gaia astrometric data, combined with radial velocity follow-up observations from ground-based telescopes, revealed another dormant black hole. This one was given the name Gaia BH2. It sits in the constellation Centaurus. Gaia BH2 has a companion star as well, but a different kind. Where Gaia BH1's companion is a sun-like star, Gaia BH2's companion is a red giant, a star that has already evolved off the main sequence and expanded considerably. The black hole itself has a mass of approximately 8.9 solar masses, somewhat less than Gaia BH1's black hole, and the orbital period of the system is approximately 1,277 days, about 3.5 years, meaning the two objects orbit each other at a wider separation than in Gaia BH1. The significance of Gaia BH2 lies in what it confirms. It's not a fluke. Gaia BH1 was not a lucky accident. The Milky Way genuinely contains dormant black holes that have remained hidden not because they don't exist near us, but because we never had an instrument sensitive enough to detect their gravitational influence on their companions. But then came the third discovery, and this one was different. In late 2023 and into 2024, another Gaia black hole candidate was announced, Gaia BH3. And Gaia BH3 was not just closer or more massive than its predecessors, it broke an entirely different kind of record. Gaia BH3 sits approximately 1,926 light-years from Earth, somewhat farther than Gaia BH1, but its black hole is estimated to have a mass of approximately 32 to 33 solar masses, 33 times the mass of our Sun. This makes it the most massive stellar mass black hole yet found in our galaxy that was detected through its gravitational influence rather than through X-ray emission. Previous X-ray detected stellar mass black holes had masses typically in the range of 5 to 20 solar masses. A 33 solar mass black hole was unexpected. But the record that matters most tonight belongs to Gaia BH1. At 1,560 light-years, it remains the closest confirmed black hole to Earth, as of our knowledge. This is shocking discovery number 2. Not only was the nearest black hole closer than expected, but it was the first of what appears to be a population of dormant, invisible black holes that have been sitting in our cosmic neighborhood undetected, for the entire history of astronomy. Let us pause here and do something that the raw number doesn't do on its own. Let us actually try to comprehend what 1,560 light-years means. A light-year is the distance light travels in 1 year. Light moves at approximately 186,282 miles per second. In 1 year, it covers roughly 5.88 trillion miles. In 1,560 years, it covers roughly 9.17 quadrillion miles. That is a 9 followed by 15 zeros. Now let's try to translate that into something more concrete. The fastest spacecraft humanity has ever launched is Voyager 1. It is currently traveling at approximately 38,000 miles per hour, about 10.5 miles per second. At this speed, Voyager 1 covers approximately 1 light-year every 17,500 years. To reach Gaia BH1 at Voyager 1's speed would take approximately 27.3 million years. For comparison, the dinosaurs went extinct about 66 million years ago. The first recognizable human ancestors, Homo habilis, appeared roughly 2.4 million years ago. We have been walking upright and making stone tools for about 2.5 million years. At Voyager 1's speed, we would cover roughly 1/10 of the distance to the nearest black hole in the entire span of recorded human evolution, from the very first stone tools to right now. But let's try a faster vehicle. Imagine we had a spacecraft capable of traveling at 1% the speed of light, far, far beyond anything we have built or could realistically build in the next century. 1% of the speed of light is approximately 6.7 million miles per hour. At this speed, you could travel from Earth to the Moon in about 2 seconds. You could cross the solar system in a matter of days. At 1% the speed of light, the journey to Gaia BH1 would take approximately 156,000 years. That is roughly twice the time that modern Homo sapiens, anatomically modern humans, have existed on Earth. Every human being who has ever lived, loved, built a civilization, written a poem, fought a war, raised a child, all of human history as we know it, would not be enough time to make this journey, even at 10% the speed of light, a velocity that would require energy inputs currently beyond our theoretical reach. The journey would take 15,600 years, even at 50% the speed of light, a velocity that no physicist has a serious proposal for achieving with any meaningful payload. The journey would still take more than 3,000 years, and Gaia BH1, remember, is the closest known black hole. When astronomers call it nearby, and they do, they are using that word in the context of a galaxy that is 100,000 light-years across. 560 light-years is a short distance within the Milky Way. It is not a short distance by any standard that connects to human experience. But here is where the story takes another turn, because the closest known black hole is doing a lot of work in that sentence. Confirmed. And the question of how complete our census of black holes actually is, that question has an answer that makes 1,560 light-years seem far less final than it sounds. Here is something that astronomers are increasingly confident about. The black holes we have found, Gaia BH1, Gaia BH2, Gaia BH3, the X-ray binaries, all of them, represent a tiny, heavily biased sample of the actual population. Let's think about the selection effects at play. The X-ray binary method finds black holes that are actively accreting material. This requires a companion star and a favorable orbital geometry. The fraction of all stellar mass black holes that happen to be in active accreting binaries is thought to be small, perhaps a few percent at any given time. The Gaia astrometric method finds black holes that have a detectable companion star and an orbital configuration that produces a wobble measurable by Gaia's instruments. This requires the companion to be bright enough to track, the orbital period to fall within Gaia's observation window, and the orbital inclination to be favorable. Gaia's mission has a limiting magnitude. Stars below a certain brightness cannot be tracked with sufficient precision. This means Gaia is essentially blind to black holes whose companions are too dim, too distant, or in orbits too wide or too narrow to produce a detectable wobble within the mission's timespan. And then there is the dominant category, Completely isolated black holes, no companion at all, drifting alone through interstellar space. These are completely undetectable by either of the methods above. The only hope for finding them is microlensing, and microlensing searches are statistical, cover limited areas of sky, and are sensitive only to black holes that happen to pass in front of a background star at the right time. So what does this mean for the true distance to the nearest black hole? The answer, according to the models, is uncomfortable. Estimates of the total number of stellar mass black holes in the Milky Way range from about 10 million to as many as 1 billion, with many mainstream estimates clustering around 100 million. The Milky Way's disk is roughly 100,000 light-years in diameter. If 100 million black holes are distributed throughout a disk that is roughly 100,000 light-years across and a few thousand light-years thick, then on average, you would expect one black hole per roughly 1 or 2 cubic light-years of galactic disk volume in the solar neighborhood. That calculation is rough and depends heavily on the local density of black holes versus the galactic average, but it suggests that the nearest isolated, undetected black hole to our solar system could be significantly closer than 1,560 light-years. Some models suggest the nearest isolated black hole could be as close as a few hundred light-years, possibly less. We simply don't know, because we can't see them. Think about what that means. Within a radius of a few hundred light-years of Earth, a region of space so relatively small that it contains only about 10,000 of the Milky Way's hundreds of billions of stars, there may be numerous black holes drifting in silence, not eating anything, not emitting anything, not revealing themselves by any means we currently have available, moving through the same region of the galaxy that we inhabit, invisible. This is shocking discovery number 3. The 1,560 light-year figure is almost certainly not the true distance to the nearest black hole. It is the distance to the nearest black hole we have been able to detect. The nearest undetected black hole, isolated, dark, silent, may be far closer. The evidence from microlensing campaigns adds another layer to this picture. Since the early 1990s, several large-scale microlensing surveys have been monitoring tens of millions of stars in the direction of the galactic bulge, looking for the characteristic brightening events that betray a massive object passing in front of a background star. These surveys, including the MACHO project, the OGLE survey, optical gravitational lensing experiment, and more recently the KMT-NET survey, have detected thousands of microlensing events over the years. Most of these events are caused by ordinary stars or brown dwarfs. Indicating a very massive lens that are consistent with the lensing object being a black hole. In 2022, a team of astronomers led by Kailash Sahu of the Space Telescope Science Institute announced a confirmed microlensing event caused by a black hole. The event, called MOA 201-BLG-191 or OGLE 201-BLG-0462, was observed by both ground-based telescopes and the Hubble Space Telescope. The Hubble data was crucial. By precisely measuring the deflection of the background star's light, the team was able to measure not just the mass of the lensing object, approximately 7 solar masses, but also its distance and proper motion. The black hole sits approximately 5,150 light-years away, farther than Gaia BH1, but the confirmation technique was groundbreaking. What matters for our purposes is what this detection revealed about the broader population. The rate at which microlensing surveys detect black hole events, corrected for the fraction of events they actually catch, versus the total that must occur, is consistent with there being millions of stellar mass black holes distributed throughout the galaxy. Imperfect as they are, paint a picture of a galaxy teeming with these objects in densities far higher than the small number of confirmed detections might suggest. And crucially, unlike X-ray binary detections or Gaia astrometric detections, microlensing does not preferentially detect black holes with companions. It detects isolated black holes, dark, solitary wanderers, the black holes that make up the vast, undetected majority of the population. The implication is clear, even if the specific number remains uncertain. There are almost certainly isolated stellar mass black holes within a few hundred light-years of Earth. Perhaps dozens of them, perhaps more. We cannot see them, we cannot point to them, we cannot name them. But our models, calibrated against everything we have detected, suggest they are there. Floating in the dark, close enough that the light they bend, if it passes through the right alignment, could in principle be detected. Close enough that they have already, invisibly, distorted the light of stars behind them as they drift through our local piece of the galaxy. Close enough that their gravity, vanishingly small at these distances but real, technically acts on every object in the solar system. Let us zoom out now, from the specific case of the nearest black hole to the broader picture of what these discoveries mean for the Milky Way as a whole. We have established that the Milky Way likely contains somewhere between 10 million and 1 billion stellar mass black holes. Let's use a middle estimate of around 100 million, a number that appears frequently in the literature and is consistent with the stellar initial mass function and the fraction of massive stars expected to collapse into black holes rather than neutron stars. In a galaxy with approximately 300 billion stars, that means roughly 1 in every 3,000 stars has a black hole counterpart somewhere in the galaxy. Or, to put it differently, if you were to pick any random star from the Milky Way and ask, is there a black hole somewhere in the neighborhood of this star? The answer would depend entirely on how large you define neighborhood. Within 100 light-years of the Sun, there are roughly 300 known stars. The volume of a sphere 100 light-years in radius is approximately 4.2 million cubic light-years. If 100 million black holes are distributed through a galactic disk volume of roughly 2.5 times 10 squared cubic light-years, then the average density is about 1 black hole per 25,000 cubic light-years. Roughly 17%. Not certain, but not negligible. Within 500 light-years of the Sun, a sphere containing thousands of stars, the probability approaches near certainty. Within 1,000 light-years, the expected number of black holes in our neighborhood is somewhere in the range of 64 to 640, depending on which estimate of the total population you use. And within 1,560 light-years, the distance to Gaia BH1, the models predict anywhere from several hundred to several thousand black holes, most of them invisible, most of them isolated, most of them completely unknown to us. What Gaia BH1 told us was not just, here is the nearest black hole. What it told us was that the detection technology had finally reached the threshold of finding dormant black holes in binary systems, the slightly less invisible subset of the full population. And if the detectable subset contains a black hole at 1,560 light-years, the undetectable majority almost certainly contains many more, potentially far closer. This is shocking discovery number 4. The nearest black hole is a ceiling, not a floor. The true nearest black hole, isolated, invisible, undetectable with current methods, is almost certainly closer. How much closer we cannot say, but the structure of the galaxy, and everything our models tell us about the distribution of stellar evolution products says that the dark ones are out there, near. At this point in any discussion of nearby black holes, a question inevitably arises. It is the question that has been quietly sitting at the back of every mind since we first mentioned proximity. What would happen if a black hole came closer? Let's be precise about this, because the popular imagination tends toward the dramatic and the catastrophic, and the reality is both more interesting and more nuanced. A black hole with a mass of 9 solar masses, like Gaia BH1's black hole, at the current distance of 1,560 light-years, exerts a gravitational force on Earth that is inconceivably small. To put it in perspective, Sirius, the brightest star in our night sky, sits about 8.6 light-years from Earth and has a mass of about 2 solar masses. The gravitational force Sirius exerts on Earth is roughly 7,000 times weaker than the gravitational force of the Sun on Earth and is completely negligible in terms of any influence on our solar system. Gaia BH1 is 181 times farther away than Sirius. Gravity drops with the square of the distance, so Gaia BH1 exerts a gravitational force on Earth that is many millions of times weaker than what Sirius already exerts. It is zero for any practical purpose. But let's think about closer approaches. Not the current distance, but what would happen if a black hole were to drift into the solar neighborhood over geological timescales? Stars pass close to our solar system regularly by cosmological standards. The star Gliese 710 is currently on a trajectory that will bring it within about 0.07 light-years of our Sun in approximately 1.28 million years. At this approach distance, Gliese 710's gravity will significantly disturb the Oort cloud, the vast, diffuse shell of icy bodies at the outer edges of our solar system. Over the following millions of years, not an immediate catastrophe, but a significant perturbation. If a stellar mass black hole were to pass at a comparable distance, 0.07 to 0.5 light-years, the effect would be similar to a stellar flyby, Oort cloud disruption, a shower of comets, an increase in the probability of large impactors reaching the inner solar system over geological timescales. Unsettling, but not immediately apocalyptic. For truly dangerous effects to occur, for the black hole's gravity to meaningfully disturb the orbits of the planets, it would need to pass significantly closer. At about 0.01 light-years, approximately 630 AU, a 10 solar mass black hole's gravitational influence would begin to meaningfully perturb the outer planets over long timescales. At 100 AU, the inner edge of the Oort cloud, far closer than any known stellar flyby, the effects on Neptune and Uranus's orbits could be quite dramatic. But the probability of such a close approach during Earth's remaining habitable lifespan is vanishingly small. The distances involved in stellar close approaches are already enormous, and actual close approaches capable of planetary orbit disruption are extraordinarily rare on any timescale relevant to life on Earth. None of this is a reason for fear, it is a reason for perspective. What a stellar mass black hole cannot do, as a matter of physics, is suck the solar system from a distance. This is the most persistent and most wrong popular belief about black holes. A black hole of 9 solar masses, if it replaced our Sun, would produce an orbit identical to what the Sun produces now. The planets would not spiral in, they would orbit normally. Black holes do not have special suction. Their gravity obeys exactly the same inverse square law as every other massive object. The only thing special about a black hole is what happens at extremely small distances from its singularity, inside the event horizon. Far from that region, it is simply a very massive, very compact, very dark object. The terror of black holes is not in their gravity at distance. It is in their existence, in what they are, in what they mean about the nature of space and matter and information, in the fact that they are out there, in the dark, in our galaxy, drifting silently through the same space we call home, not waiting for us, not moving toward us, simply existing. We have been speaking of black holes with a certain assumption of shared understanding, that the listener has a working mental model of what a black hole actually is. But the reality of a black hole, examined closely, is stranger than any casual description can convey. And in the spirit of granular immersion, of truly understanding what we are discussing when we discuss nearby black holes, let's spend time here. A black hole is a region of space-time where gravity is so intense that the escape velocity exceeds the speed of light. The event horizon is the boundary of this region, not a physical surface, not a wall, not a membrane, but a mathematical surface in space-time. If you were approaching a stellar mass black hole and crossed the event horizon, you would not feel a physical barrier. You would not be shredded at the moment of crossing. You would simply continue falling inward toward the singularity. And from that moment on, your future, every possible future consistent with the laws of physics, would lead inward. Not because you are being pulled with irresistible force, but because space-time itself, inside the event horizon, is structured so that all directions point toward the singularity. There is no outward path. The geometry of space-time is what traps you, not a force. For a black hole with the mass of Gaia BH1, approximately 9.62 solar masses, the event horizon has a radius of approximately 28.4 kilometers. That's about 17.7 miles. The entire region from which no light can escape is a sphere roughly 35 miles in diameter, smaller than many cities. On the scale of a solar system, it is a speck. Of Los Angeles. Beyond the event horizon, but at distances comparable to the event horizon radius, the effects of extreme gravity become dramatic. A phenomenon called tidal forces, the same basic physics that creates ocean tides on Earth, produced by the slightly stronger gravity on the near side versus the far side of an object, would become lethal near the event horizon. For a stellar mass black hole, an infalling astronaut would be stretched lengthwise and compressed laterally, a process physicists describe with the delightfully grim term spaghettification. The tidal forces at the event horizon of a 10 solar mass black hole are sufficient to destroy any known material long before the event horizon is reached. The exact distance at which spaghettification kills a human body depends on the specifics, but it would occur at roughly 400 to 1,000 kilometers from the singularity, well outside the event horizon. This is interesting and worth sitting with for a moment. Supermassive black hole. For M87, 6.5 billion solar masses, the event horizon has a radius of roughly 12 billion miles. The tidal forces at that event horizon are mild. A human body could theoretically cross the event horizon of a supermassive black hole and not immediately be destroyed. They would have no way to escape, and the singularity would be their eventual fate, but the crossing itself would not kill them immediately. For the black holes in our neighborhood, 9 solar masses, 33 solar masses, the event horizon is violent. The tidal forces are crushing at any approach. Up close, these objects are as dangerous as their reputation suggests. From 1,560 light-years away, they are harmless. Less than harmless, they are invisible. Beyond the optical and astrometric methods we have discussed, there is one other detection technique that deserves extended attention in any thorough treatment of black holes. It is the newest, the most dramatic, and in some ways the most profound. It is gravitational wave detection. When two black holes spiral toward each other in a binary system, they do not simply orbit each other in silence. General relativity predicts that any accelerating mass will emit gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light in all directions. For ordinary masses, these ripples are inconceivably tiny. A human walking produces gravitational waves, in principle, but they are so weak that no instrument could conceivably detect them. But for massive compact objects like black holes, the gravitational waves emitted during the final moments of a merger can be enormous. Enormous in the context of gravitational waves, which still means that by the time they reach Earth, they represent a distortion of space smaller than 1,000th the diameter of a proton. On September 14, 2015, at 5:51 in the morning Eastern US time, the two detectors of the LIGO experiment, one in Livingston, Louisiana, one in Hanford, Washington, registered a signal. The signal lasted about 1/5 of a second. It began as a slow oscillation and then rose rapidly in frequency and amplitude before cutting off, a characteristic chirp pattern. The signal, when played through a speaker, sounds like a brief, rising tone. This was the first direct detection of gravitational waves. The source? Two black holes, with masses of approximately 36 and 29 solar masses, merging approximately 1.3 billion light-years away. The energy released in gravitational waves during that fraction of a second was greater than the total energy output of all the stars in the observable universe combined for that same fraction of a second. Detector arms, 4 kilometers long, by a distance less than the diameter of a proton. LIGO and its partner detector Virgo have since detected dozens of additional gravitational wave events, black hole mergers, neutron star mergers, mixed events, each one a message from the violent cosmos, carried by the bending of space-time itself. But gravitational waves are currently detectable only from merging compact objects, the final moments of a binary in spiral, when the objects are extremely close and moving at a significant fraction of the speed of light. Isolated black holes, sitting quietly in our galactic neighborhood, produce no gravitational waves. They are dynamically inactive. The only gravitational wave signal from our nearest black hole will come, if it comes at all, billions of years from now, if it eventually encounters another compact object in a long, decaying orbit. For now, the nearest black hole is silent to our gravitational wave detectors as well. There is, however, a future generation of gravitational wave detector that may change this. The proposed LISA mission, the Laser Interferometer Space Antenna, would consist of 3 spacecraft in a triangular formation, separated by roughly 2.5 million kilometers. LISA would be sensitive to gravitational waves at much lower frequencies than ground-based detectors, making it capable of detecting not just mergers, but long-period binary systems. A black hole in a decades-long binary orbit with a neutron star, for example, would emit gravitational waves at low enough frequency to be potentially detectable by LISA. This would open an entirely new window onto the dormant black hole population in our galaxy, including, potentially, objects much closer than any we have found. The nearest black hole we know about is almost certainly not the nearest one that exists. Let's step back for a moment and trace the intellectual history of how human beings came to understand that such things as black holes could exist. Because this history is not a story of steady progress. It is a story of ideas that were accepted and then doubted, of equations that implied things their authors refused to believe. But in 1783, a British clergyman and natural philosopher named John Michell, largely forgotten by history, yet one of the most original scientific minds of his era, was thinking about light and gravity. Newton's theory of gravity was at that time the authoritative description of gravitational physics. Light was understood, by Newton and his contemporaries, to consist of particles, corpuscles, with some small but finite mass, and gravity acts on all mass. Michell performed a simple calculation. If a star were massive and dense enough, its escape velocity, the speed an object would need to reach to escape its gravitational pull, might exceed the speed of light. A light corpuscle launched from the surface of such a star would slow down as it climbed the gravitational well, just as a ball thrown upwards slows down under Earth's gravity. If the star were dense enough, the ball, or the light corpuscle, would reach zero velocity before escaping and fall back. Michell called these objects dark stars. He calculated that a star with the same density as the Sun, but 500 times its radius, would have an escape velocity equaling that of light. Light from such a star could not escape. It would be invisible. This was the first theoretical prediction of what we now call a black hole. It was made 133 years before Einstein published general relativity, and it was essentially ignored for over a century. Einstein published his general theory of relativity, a complete reimagining of gravity, not as a force but as the curvature of spacetime caused by mass and energy. Within months, a German physicist named Karl Schwarzschild, working on the front lines of World War I, found an exact solution to Einstein's field equations, a mathematical description of the spacetime, a perfectly spherical, non-rotating mass. In this solution, there was a special radius, now called the Schwarzschild radius, at which the geometry of spacetime became singular. At this radius, the metric terms in Einstein's equations diverged to infinity. Schwarzschild himself did not know what to make of this singularity. He considered it a mathematical artifact, a quirk of the equations, not something physically real, Einstein agreed. In 1939, Einstein published a paper explicitly arguing that Schwarzschild singularities do not exist in physical reality. He argued that no physical process could compress matter to the density required to form one. He was wrong. In the same year, 1939, Robert Oppenheimer and Hartland Snyder published a paper showing that a sufficiently massive star, when it exhausted its nuclear fuel, would undergo a runaway gravitational collapse. There was nothing in known physics to stop it. The collapse would proceed through the Schwarzschild radius. A true singularity would form. Oppenheimer and Snyder's paper was largely overlooked. The physics community was distracted by World War II, by atomic physics, by radar. And the term black hole did not yet exist. It was coined by the physicist John Wheeler in 1967. It was not until the 1960s that the theoretical understanding of black holes matured into something approaching the modern picture. The discovery of quasars, enormously energetic objects at the centers of distant galaxies, now understood as active supermassive black holes consuming matter at prodigious rates, forced the community to take black hole physics seriously. Roger Penrose proved in 1965 that singularities were an inevitable consequence of gravitational collapse under very general conditions, not a special case artifact. Stephen Hawking extended this work and proved the area theorem, that the total event horizon area of a system of black holes could never decrease. And in 1974, Hawking made his most famous theoretical contribution. By applying quantum mechanics to the vicinity of the event horizon, he showed that black holes are not perfectly black. They should emit a faint thermal radiation, now called Hawking radiation, arising from quantum effects at the event horizon. For stellar mass black holes, this radiation is so unimaginably faint, a temperature of less than a millionth of a degree above absolute zero, that it is completely undetectable by any conceivable instrument. But theoretically, it means that black holes are not permanent. Over timescales so long they make the current age of the universe look like an eye blink, stellar mass black holes would slowly evaporate. The timescale for a 10 solar mass black hole to evaporate via Hawking radiation is approximately 10 to the power of 67 years. For context, the current age of the universe is about 1.4 times 10 years. Effectively, for any purpose relevant to the observable universe's remaining lifetime, stellar mass black holes are permanent. They will outlast the stars. They will outlast the galaxies. They will drift through the cooling, darkening, expanding universe for timescales that dwarf every other timescale in astrophysics. The black holes that exist in our galaxy today, including the ones in our local neighborhood that we have found, and the far greater number we have not, will still exist when the last star in the universe burns out, still exist when the protons that make up ordinary matter have decayed, still exist, slowly draining through Hawking radiation, in a universe so cold and empty and dark that no conventional matter remains. This is what we are measuring the distance to, not just a dramatic astrophysical object, something that will outlast almost everything else in the universe. There is one aspect of this story that we have not fully explored, and it deserves its own space. Because the story of Gaia BH1 is not just the story of a black hole, it is the story of a relationship. The sun-like star that orbits Gaia BH1 has been doing so for a very long time. The binary system is estimated to be quite old. The black hole formed from a massive star that lived and died billions of years ago. Since that formation event, the companion star has been in orbit. It has circled the black hole through every major event in galactic history, through the formation and death of nearby stars, through the quiet expansion of the Milky Way's spiral arms, through all of the biological history of Earth, every extinction, every emergence, every evolutionary leap, from single cells to complex multicellular life, to the first nervous systems, to the first eyes, to the first creatures that looked up at the night sky. Through all of that, the companion star has orbited, a 186-day rhythm, steady, indifferent. The star does not know it orbits a black hole. It simply falls perpetually around a center of gravity it cannot see. This is worth sitting with. When we say the nearest black hole is 1,560 light-years away, we are not just specifying a location. We are describing a relationship that has persisted across geological time. A star and its dark twin, bound together by gravity, tracing their mutual orbit through the quiet dark. And the star is not in danger, not currently. It orbits at a distance far too great for the black hole to strip material from it. Unlike in an X-ray binary, where the companion is so close that the black hole's gravity overwhelms the star's own surface gravity and pulls matter away, Gaia BH1's companion orbits at a safe remove, roughly the same distance as Venus orbits our Sun, though the orbital dynamics are different. The star's material stays on the star. The black hole remains dark. But the companion star is not static, it is aging. All stars age. Our Sun-like companion will, in roughly 5 to 6 billion years, begin the process of expanding into a red giant. When that happens, its outer layers will extend much farther into space. And as those layers expand, they will begin to approach the boundary where the black hole's gravity begins to compete with the star's own self-gravity. At some point, material from the expanding star's outer envelope will begin to fall toward the black hole, and when that happens, Gaia BH1 will wake up. Silent black hole that has drifted invisibly through space for billions of years will suddenly have a food source. An accretion disk will form. X-rays will pour outward. The system will become what astronomers call an X-ray binary, the same type of system we detected Cygnus X1 as. Back in 1971, in roughly 5 to 6 billion years, the nearest known black hole will transform from the quietest object in our neighborhood to one of the brightest X-ray sources in the galaxy. And Earth will not be here to see it. Our Sun will have also expanded into a red giant by that time, having long since consumed the inner planets and rendered Earth uninhabitable. Whatever humans, they will be observing from somewhere else entirely. The system they will observe, blazing in X-rays across 1,560 light-years, will be the same system that spent all of human history sitting in quiet, invisible darkness. Nothing in the universe lasts, but some things last longer than others. We have covered a great deal of ground tonight, but any honest treatment of this subject must also confront the edges of our knowledge, the places where the story becomes genuinely uncertain. The most honest answer to the question, how close is the nearest black hole, is closer than 1,560 light-years, but we don't know how much closer. The most honest answer to how many black holes are in our immediate galactic neighborhood is probably dozens to hundreds within 1,000 light-years, but we have only confirmed a handful. The most honest answer to do any of these black holes pose a danger to Earth is almost certainly not within any timescale relevant to human civilization or biology, but we cannot exclude extremely improbable close encounters on multi-million-year timescales. And the most honest answer to will we ever be able to directly observe an isolated stellar mass black hole is probably Eventually, with sufficiently advanced technology, but not yet, there are deeper uncertainties as well. The exact mechanism by which Gaia BH1 formed, without disrupting its binary companion in the supernova explosion, is not well understood. The distribution of natal kicks in black hole formation is poorly constrained. The fraction of massive stars that produce black holes versus neutron stars versus direct collapse without any supernova is still actively debated. And there is one question that haunts the field in a particularly interesting way. Are there black holes even closer than the models suggest? Some theorists have proposed that the early universe, in the moments after the Big Bang, might have produced black holes through a different mechanism entirely, not from stellar collapse, but from density fluctuations in the primordial fireball. These primordial black holes could have masses ranging from asteroid-sized to stellar mass. They would have formed long before any stars existed, and if they exist in significant numbers, they might be distributed throughout the galaxy in a pattern quite different from the stellar mass black holes formed from stellar evolution. The evidence for primordial black holes is currently inconclusive. They have not been confirmed, but they have also not been ruled out across all mass ranges. If primordial black holes with masses of a few solar masses exist and are distributed randomly through the galaxy, some of them might be extraordinarily close, closer than any stellar mass black hole we have found. This is pure speculation at this stage, but it is the kind of speculation that the science takes seriously, that keeps the question open, that keeps the search ongoing. We don't know, but the not knowing is the most interesting part of the whole story. The story of finding nearby black holes is not finished. It is, in many ways, just beginning. The Gaia mission continues to collect data, and the full catalogue from the extended mission will contain far more astrometric time series data than the first releases. Preliminary analyses suggest that several dozen additional black hole candidates in binary systems may be identified in future Gaia data releases. Each new detection adds to our census, refines our understanding of black hole formation efficiency, and potentially brings the confirmed nearest black hole closer. Beyond Gaia, the Roman Space Telescope, formerly the Wide Field Infrared Survey Telescope, scheduled for launch in the mid-2020s, will conduct a major microlensing survey toward the galactic bulge, monitoring hundreds of millions of stars for microlensing events. The Roman telescope's cadence and sensitivity are expected to detect thousands of microlensing events, with a significant fraction expected to be caused by black holes or neutron stars. Unlike previous surveys, Roman will have sufficient photometric precision and cadence to measure the astrometric shift associated with the lensing, the actual deflection of the source star's position, not just the brightening. This allows a direct measurement of the lensing object's mass and distance, rather than just a statistical estimate. Roman's microlensing survey is expected to detect dozens to hundreds of black holes through this method. It will, for the first time, provide a direct, statistically significant sample of isolated stellar mass black holes, and given the spatial volume it will probe, primarily toward the galactic center, but also including portions of the galactic disk, it will dramatically improve our estimates of black hole density in the galaxy. Then there is the next generation of X-ray observatories. The proposed Athena mission from ESA, the Advanced Telescope for High-Energy Astrophysics, would be far more sensitive than current X-ray telescopes, potentially detecting X-ray binaries too faint or too distant for current instruments to characterize. This would expand the confirmed population of X-ray bright black holes and provide better constraints on the active accreting fraction. And in the longer term, there is LISA, the space-based gravitational wave detector we mentioned earlier, which would be sensitive to the low-frequency gravitational waves produced by long-period binary systems involving compact objects. LISA could, in principle, detect a stellar mass black hole orbiting a neutron star in a decades-long binary within a few thousand light-years, a class of system that is completely invisible to all current detection methods. Is of a galaxy far richer in black holes than any previous generation imagined. And as the instrumentation improves, as the census grows, the distance to the nearest known black hole will almost certainly shrink further. The current record of 1,560 light-years will likely be broken, possibly more than once. How close will the nearest confirmed black hole eventually be? It is genuinely difficult to predict, but astronomers who work on this question privately acknowledge that finding a confirmed black hole within 1,000 light-years would not be surprising. Finding one within 500 light-years would be extraordinary, but not impossible. Calibrated against what Gaia has already found, suggests that the galaxy is generous with these objects in our neighborhood. The darkness around us is more occupied than we thought. Let's just spend a moment with the numbers. 1,560 light-years, the nearest known black hole. The light you see when you look at the night sky, from most of the stars visible to the naked eye, left those stars decades or centuries ago, at most. The light from Sirius left 8.6 years ago. From Betelgeuse, roughly 700 years ago. These are the near stars. Ancient light, by human standards, but recent by cosmic ones. The light from Gaia BH1's companion star that reaches your eye tonight left that system 560 years ago. The year was approximately 465 CE. The Western Roman Empire had one more year to exist before the conventional end date of 476 CE, when the last Roman emperor in the West was deposed. The Gupta Empire in India was nearing its peak. The Maya civilization in Mesoamerica was constructing the great temples of Tikal. There was no Islam yet. There was no printing press. There was no concept of what would become modern science. The people alive in 465 CE could not have known that the light leaving that distant star system in their era would arrive at Earth in a time when their descendants would have instruments capable of detecting the wobble of a star orbiting an invisible dark object. And yet the light left. And it traveled for 1,560 years, through interstellar space, past other stars, through the thin gas of the Orion Arm, arriving now at the photon receptors of the Gaia telescope's focal plane, carrying the information, encoded in the direction of its approach, accumulated over millions of measurements, that tells us a black hole is there. When we say we found the nearest black hole, this is what we did. We caught light that has been traveling since the fall of Rome, analyzed the path of the star it came from, with instruments of almost incomprehensible precision, and inferred from the gentle wobble in that star's position the presence of a 9.62 solar mass dark object that has been drifting through space since long before any human civilization existed. This is what science is: patient, precise, humble before the scale of what it is trying to understand. And the nearest black hole, this ancient, dark, silent thing drifting 1,560 light-years away, has been there the whole time. Through all of human history, through every civilization and every war and every poem and every night sky that any human has ever looked up at and felt small, it was always there. We just didn't know. There is a particular kind of comfort and a particular kind of vertigo that come from understanding this story fully. The comfort comes first. The nearest black hole is 1,560 light-years away. In human terms, in any terms that matter for daily life or for the span of civilization, this is effectively infinite. It poses no danger. It exerts no measurable influence on our solar system. It does not threaten us in any physical sense. The universe has placed this extreme object at a distance that renders it harmless, a thing to observe, to wonder at, to calculate, but not to fear. But the vertigo comes when you shift the frame slightly, because 1,560 light-years, while vast by human standards, is remarkably small by galactic standards. The Milky Way is 100,000 light-years across. Gaia BH1 sits in our same galactic arm, the Orion Arm, just a little farther along its curve. We and Gaia BH1 are essentially neighbors, cosmic neighbors, the kind of neighbors who live across town and whose existence you are dimly aware of. And beyond that one confirmed neighbor, the 1,560 light-year marker, there are models that suggest dozens more in the same volume of space, dark, silent, invisible, moving through interstellar space on trajectories shaped by stellar birth and death events that occurred billions of years ago. We share the galaxy with millions of them. This is worth sitting with, not as a source of fear, but as a source of wonder. The universe does not confine its most extreme objects to remote corners. It distributes them throughout. In every region of a galaxy like ours, drifting among the ordinary stars, there exist these remnants of stellar deaths, objects where matter has been compressed beyond any state we can produce in a laboratory, where space-time curves so sharply that geometry itself breaks down, where the physics we understand stops applying and something stranger takes over, and we notice them. Not all of them, nowhere near all of them, but some. Through the careful analysis of starlight, through the precise measurement of stellar wobbles, through the patient monitoring of millions of stars for the signature brightening of microlensing, through the detection of space-time ripples from binary mergers a billion light-years away, we are building, slowly and carefully, a map of the dark things in our galaxy. There is something profound in this that goes beyond the science. We are creatures of extreme improbability, assembled from matter created in stellar cores, residing on a small, rocky world orbiting an ordinary star, equipped with nervous systems of staggering complexity that somehow generate not just sensation but understanding. We live on a scale so far removed from the quantum that we cannot feel individual atoms, and so far removed from the cosmic that we cannot feel the galaxy rotating beneath us. We are intermediate creatures, suspended between extremes we cannot directly experience, and yet we can measure them. We can construct instruments so precise that they detect the wobble of a star being gravitationally tugged by an invisible dark object. 560 light-years away, we can build detectors that register the passage of a gravitational wave, a distortion of space-time smaller than a proton, from two black holes merging a billion light-years distant. Must contain millions of black holes, most of them invisible, and then design missions to look for them and find them. This is a remarkable thing to be able to do. Unreasonably remarkable. There is no survival advantage in knowing that a black hole is 1,560 light-years away. There is no direct practical application of this knowledge. It changes nothing about how we live, or what we eat, or how we raise our children. And yet we have built the entire infrastructure of modern science. The telescopes, the satellites, the algorithms, the international collaborations, the decades of patient observation to answer exactly this kind of question. Because we want to know. Because knowing feels like something. Because the universe is vast and strange, and we are the part of it that is trying to understand the rest of it. That is not nothing. That is, in fact, everything. "560 light-years from where you are right now, a sun-like star is completing an orbit. It has been doing this for billions of years. Right now, as you listen to these words, it is tracing its path around a center of gravity that is dark and invisible and silent. Stars do not know things. They simply burn, and orbit, and in time, die. The black hole at the center of that orbit has been waiting there since long before the Earth existed. It formed when a massive star exhausted its fuel and collapsed, an event that would have briefly made a single point in the Ophiuchus region blaze with supernova light brighter than a galaxy. Then the light faded. The black hole remained, and it has been drifting, quietly, through the same galactic neighborhood ever since. through the formation of our solar system 4.6 billion years ago, through the emergence of liquid water on Earth, through the first cells, the first multicellular organisms, the first creatures with eyes, the first creatures that could look upward and wonder, through the evolution of hominids on the African savanna, through the domestication of fire, through the invention of agriculture and writing and mathematics and telescopes, through all of it, Gaia BH1 has been there, dark, silent, drifting. We found it in 2022, not because it announced itself, not because it moved toward us or did anything dramatic, but because we had finally built an instrument, a satellite in a gentle orbit around the Sun, measuring the positions of nearly 2 billion stars with micro-arcsecond precision, that could detect the tiny, patient, gravitational whisper it leaves on its companion star, and it is the closest one we have found, not the closest one that exists. That one, the actual nearest black hole, isolated, invisible, dark, is somewhere out there that we cannot yet point to. It has no name. It has no coordinates in any catalogue. It is somewhere between Earth and Gaia BH1, possibly much closer than 1,560 light-years, sitting in the dark with the infinite patience of a thing that has no awareness of time at all. We are looking. We will keep looking. As our instruments improve, as our models are refined, as each new detection adds another data point to the census we are building, we will continue to map the dark things in our galactic neighborhood. The nearest one will eventually be found, and then a still nearer one after that. Because they are there, the models are sure of this, and eventually the technology will be good enough to reveal them. Until then, they drift, and we build. And the distance between us, whatever it actually is both vast and intimate. Vast because 560 light-years exceeds any distance we have traveled or could travel in any timescale relevant to our civilization. Intimate because in the context of a galaxy 100,000 light-years across, we and these dark remnants of dead stars are essentially in the same place, sharing the same curved arc of the Orion Arm, moving together, slowly, in the Milky Way's great rotation, separated by distances that feel enormous and are, cosmically, barely a separation at all. We are not even alone in our immediate galactic neighborhood. We share it with the remnants of ancient stars, collapsed, dark, invisible, silent, drifting through the same space we call home. This is not a frightening thing, if you let it settle. It is a humbling thing, a reminder that the universe is older and stranger and more densely inhabited than the comfortable, star-filled view from Earth suggests. That the dark between the stars is not empty, that the silence is not absence. There are things out there that have outlasted almost everything else, that will outlast almost everything to come, and the distance between us and the nearest one, whatever it actually is, whether it is 560 light-years or 500 or 200, is both the answer to a scientific question and a kind of philosophical fact. We exist in a universe that contains such things, and we are the part of that universe that knows it. Tonight we explored the distance between us and the nearest black hole, and what we found was not a simple number. We found that the nearest known black hole, Gaia BH1, in the constellation Ophiuchus, sits 1,560 light-years away. That this was a surprise. That previous estimates put the nearest black hole at roughly twice that distance. That the discovery was made not through X-rays or explosions, or any of the dramatic signatures astronomers had previously relied on, but through the extraordinary precision of the Gaia Space Telescope detecting the subtle gravitational wobble of a companion star. We found that 1,560 light-years is both incomprehensibly far and, within the context of our galaxy, nearby. That it would take 27 million years to reach at Voyager 1's speed. That it would take 156,000 years, even at 1% the speed of light. We found that the confirmed population of nearby black holes is almost certainly a small, heavily biased fraction of the true population. That isolated, dormant, invisible black holes almost certainly exist within our immediate galactic neighborhood, perhaps within a few hundred light years, undetected by any instrument we currently possess. We found that this situation will improve, that upcoming telescopes and missions, Roman, LISA, next-generation X-ray observatories, will expand the census, will push the confirmed nearest black hole closer, will reveal in time the full extent of our dark neighborhood. And we found something harder to quantify but no less real, that the distance between us and the nearest black hole is not just a measurement, it is a reminder of how large the galaxy is and of how small we are within it, of how much remains undetected, unnamed, uncatalogued in the dark between the stars, of how remarkable it is that we can look into that dark at all, that we have built the tools and the knowledge and the sustained collective curiosity required to ask questions like this and actually make progress toward answers. The nearest black hole has been there since before Earth existed. It will be there long after the last human civilization has faded. In its own way, it is the most enduring thing we have ever pointed a telescope at, and it sits there, 1,560 light-years away, exactly as indifferent to our observation as it has always been. But we noticed it. And noticing, pointing at the dark and saying, there is something there, let me try to understand it, is what we do. It is perhaps the most distinctly human thing we do. The universe is old, and dark, and vast, and full of things we have not yet found, but we are finding them, one wobble at a time, one light-year at a time. Sleep well tonight, knowing that the nearest black hole is exactly where it has always been, and knowing that somewhere, right now, an instrument is quietly watching a star, measuring its position, tracking its wobble, patient across the years, looking for the next dark thing in the neighborhood, and eventually it will find it. Good night, and rest well beneath the stars.